Hello, everyone. Thank you for joining the Canadian Underground Infrastructure Innovation Center Academy webinar. My name is Inshik, and I'm today's moderator. And today's webinar is titled Underground Infrastructure Innovations from CUIIC and Clemson University, Lifecycle GHG Assessment and Seismic Resilience via CIPP. Organized by the Canadian Underground Infrastructure Innovation Center, the University of Alberta, and Benjamin Media, CUIIC Academy offers classes, courses, webinars, and events to help further underground infrastructure educational opportunities across Canada. CUIIC Academy webinar happens every third Thursday of each month. So please join us for our next installment in April 16th this year. And registration for the CUIIC Academy Fall Summit is going to open soon, which is going to be held in September 15th to 17th in Vancouver, British Columbia. So if you want to know more about it, please visit CUIIC.ca to learn more. And thank you very much for Ackerman for being 2026 webinar series sponsor. And now let me introduce our speakers today. First of all, I'll go with Mahmoud. Mahmoud Yadullahi is a PhD candidate in construction engineering and management in the Department of Civil Engineering at Clemson University. His research focuses on the seismic performance and management of buried water pipeline infrastructure, with particular emphasis on water distribution system resilience and secured in place pipe CIPP rehabilitation. He has a background in structural and earthquake engineering and employs fragility modeling, network level resilience analysis, and probabilistic assessment methods to evaluate infrastructure vulnerability under earthquake loading. His work aims to support data-driven rehabilitation planning and resilience-based decision-making for water distribution system. Mahmoud holds a master's degree in structural engineering with a focus on seismic performance assessment of buildings and damping technologies. Now let me introduce Freddie, who is the second presenter. Freddie A. Diaz-Duran, PhD, is a postdoctoral fellow in civil and environmental engineering at the University of Alberta. He earned his PhD in civil engineering geotechniques from the University of Waterloo and has directed industry-partnered projects, led research initiatives, and taught and supervised student teams in dynamic soil characterization, slope and excavation stability, and sustainability LCA for subsurface works. His current work advances computational geomechanics, geohazard assessments, and risk analysis for resilient underground and geotechnical infrastructure, integrating field and laboratory characterization with numerical modeling and statistical probabilistic methods to enable risk-informed decision-making under uncertainty. He translates ground structure interaction into clear performance ranges and design margins for a wide spectrum of systems and contexts, including linear corridors and utilities, trenchless works, tunnels, foundations, and geohazard-prone sites in municipal, energy, and transportation settings. So please welcome our presenters, and Mahmoud, now the floor is all yours.
Awesome. Thank you very much, Justin. Hello, everyone. Thank you for the introduction. My name is Sayed Mahmoud Yadullahi, and I'm here to present parts of my research in Clemson University on investigating seismic resilience improvement of water mains using CIPP lining. Just a quick uh, overview or introduction of myself. I'm a PhD candidate and pipeline infrastructure researcher in Clemson University. I hold a structural master degree studying seismic assessment of buildings, and I also, as a structural researcher, I collaborated with Technical University of Munich and Garver Water Design Center. So here's just a quick overview of today's presentation. First, we're going to discuss some introductory slides talking about earthquakes and pipelines in general and the goals of our research. And then we're going to go to the second phase of this study. First phase of this study about finite element modeling and developing fragility models. And then we're switching to the second phase, which is network resilience assessment and considering CIPP rehabilitation. So water distribution systems are very critical lifelines all around the world. However, seismic events expose their vulnerability during different events. For example, in 1994 Northridge earthquake, more than 70% of Los Angeles transmission systems have been disrupted. Or in 2011 Christchurch earthquake, the city experienced thousands of pipeline failure and the recovery of the whole system took more than 3 years. In another incident at 1989 Loma Prieta, the city had to replace 60,000 feet of water main and 1,700 services. There are many other incidents and events that exposing the vulnerability of buried pipelines, like 99 Kokeli, 95 Kobe, and 2015 Gorka earthquakes. However, we're not going to dig deep into each of these events. But the one thing that we can learn about this is that one of the pipe material that failed the most during these events was cast iron pipes. Let's talk about cast iron pipes and why we focused on these type of pipe material. Around 50% of North American water mains are built from cast iron pipes and cast iron material, and a lot of which are very old and they are expected to be severely deteriorated. So in case of an earthquake happening, we can expect a lot of failure for this pipe material on our water mains. And the past events shows that among all pipe material, cast iron, as we mentioned previously, has the highest seismic failure rates. And also the primary failure mode of these pipes are joint pull-out mode, which is occurring as a type of a joint failure mode. We can rehabilitate these aging cast iron pipelines through CIPP or cured in place pipelining technology, which is a widely used trenchless rehabilitation technique. And a recent survey by mid 2010s showed more than 40,000 miles of CIPP rehabilitated pipes globally, and we expect that this number is much higher these days. It's basically in this method, it installs a resin saturated liner in a deteriorated or cracked cast iron pipe. The thing that we need to know is that there are limited seismic fragility studies on CIPP pipes, and there is a good gap for research in this area. Another question that we have to answer is network level analysis and why we perform network level instead of focusing on segmented pipes. Failure uh, on an for water main for water network, failure of a pipeline can propagate across the network. and disrupt the connectivity, service path, and the whole demand satisfaction. And the damage basically is not focused on the single pipe, rather it propagates through the system. So in order to evaluate this resilience of the system, you need to perform network level analysis in order to learn about critical links or critical pipes that affecting your network the most and be able to come up with informed rehabilitation or recovery planning and strategies. The research gap basically that we wanted to pinpoint and address in this study was the current literature are offering a generic fragility relations for cast iron pipes. It means they do not cover a wide range or different range of pipes, or they do not include different soil classifications. And there's a huge gap for cast iron rehabilitated with CIPP fragility relations. On the other hand, the available network level resilience were limited to those available generic relations. And also, another important gap is that the current literature does not cover the CIPP rehabilitation strategy on a network level, which is a very good gap that we are aiming to cover and address. Now let's start talking about the first phase of my study, which is seismic assessment of CIPP lined cast iron pipes. Here, we're going to discuss uh, finite element modeling of pipelines, performing IDA or incremental dynamic analysis, and also trying to develop an attempt to develop generate diameter and soil specific fragility relations and fragility curves. So the methodology here was to develop three sets of 3-kilometer pipelines, a 2D FE model for 150, 300, and 40 millimeter diameter, or in another unit, 6, 12, and 16-inch pipes. They were built with lead caulk joints, which is a most common joint for water mains, for cast and water mains. And for CIPP material, we use Starline 2000 liner, which is an industry representative liner. For soil classes, we include soil class B, C, and D per ASC is 7, and we use the American Lifeline Alliance or ALA's common and popular soil pipe interaction behavior model. And to perform IDA, 3 sets of 12 near ground motion records have been applied to the model. 3 sets, each for a certain soil classes. One for soil class D, one for soil class C, and the other one for soil class B. After developing the model, we simply cannot use the model without validating it, right? We need to make sure that this model works reasonably and the results that it produces make sense. So for validation purposes, using the same methodology, we remodel a 1 mile long buried cast iron pipes, and we compared our results with experimental and numerical results and outputs from 2 different authors from their published works, and our results seated right between both experimental and numerical results, showing that our results can be reliable both experimentally and also numerically. Now let's talk about the results that we developed here. So as I mentioned, one of the main goal of this phase was developing fragility relations. And fragility relations is nothing but calculating the repair rates, meaning the number of repairs per kilometer per different seismic level. In this case, per different ground strain. We developed these relations for 3 different soil classes, soil class B, C, and D, for 6-inch pipe, 12-inch, and 16-inch cast iron pipes, both with and without CIPP. And we're going to use this for this second phase. However, let's discuss some minor results that we can get by just looking at these plots, shall we? For example, in the low moderate seismic demands, the cast iron pipes have showing the repair rates of 1 to 3 joints per kilometer. However, for CIPP, this repair rate is less than 1. On the other hand, in the case of very severe seismic events, the cast irons are experiencing between 10 to 20 joints failure per kilometer, which is a very huge and very costly failure to cover. On the other hand, in the case of CIPP line pipes, these repair rates are less than 5. So we use these relations to develop some regression models for 3 sets of soil and 3 sets of pipe sizes for with and without CIPP. Again, for 6, 12, and 16 inch, and for different soil classes. Another set of results that we can discuss was repair rates versus ground velocity. So in previous plots, in previous fragility relations, we had repair rates per ground strain. This time, we developed repair rates per ground velocity for CIPP, and it shows that softer soil basically having higher repair rates for CIPP line pipes. And these difference, these higher repair rates are most pronounced at very high seismic demands and very high PGV, mostly above 200 centimeter per second, which is basically represent a very strong seismic event. Now let's use our relationships from phase 1 and start phase 2, which is network level seismic resilience assessment and CIPP rehabilitation. Our goal here is simply using the phase 1 fragility relations for our network assessment, developing random seismic scenarios, performing sensitivity analysis, and also considering and developing budget constraint CIPP rehabilitation plan. In order to do so, our methodology is projecting water networks benchmarks, namely D-Town and XNet, which are famous benchmark water networks, onto Charleston, South Carolina. And why Charleston? Because in South Carolina, Charleston considered as the highest seismic hazardous area for the whole state here. After projecting our water networks there, we developed 10,000 random seismic scenarios for earthquake with moment magnitude of 8. We collected our soil classes from available GIS datasets. Another things to mention is that since our model is focused on cast iron pipes, all network pipes modeled as cast iron. In order to simply explain the methodology here, do the sake of our limited time here, what we did was calculate the ground velocity using the GMP available ground motion prediction equation models for Eastern America. Then use these velocity to calculate the ground strain, and through that, calculating the repair rates that each pipeline is experiencing. And from that repair rate, calculating failure probability, and basically each of these is using a simple output from previous step into a new formulation. And then use those failure probability for all the network pipelines to calculate the seismic resilience of the whole system. And through these steps, we are using the developed fragility relations from the first phase. Now let's talk about the results. So our results for 10,000 seismic scenarios for each of XNet and D-Town water distribution systems shows that XNet the bigger XNet, which was the bigger water network, was showing the average of 59.4% seismic resilience. On the other hand, DTON, which was basically the smaller scale water network, was showing a 66.7% seismic resilience. One thing that we need to know that these numbers with themselves doesn't mean that much, doesn't mean anything. And what we are going to do with this and what we learn from this would be meaningful. For example, the sensitivity analysis that we performed was basically trying to see how our system was sensitive to pipe diameter, epicentral distances, and magnitude and soil stiffness. In other words, we wanted to check how much each of these parameters are affecting our final results. According to the sensitivity analysis results, soil stiffness and earthquake magnitude are affecting our results the most, following by epicentral distances. And surprisingly, pipe diameter, which one might think affect the system the most, on the other hand, affects the system the less. And this was a very interesting observation here. Basically, it means if you want to calculate the seismic resilience of your area, of your network, the more accurate results that you can get from your soil classes, from your earthquake properties, would give you the most accurate results. In another part of our results, we selected the worst case seismic scenario from those 10,000 random seismic events, and we tried to assign a constraint budget to see how much CIPP rehabilitation can improve the seismic performance of the system. In the case of XNet, on the left part of this slide, we assigned a 50 million constraint budget. And after performing genetic algorithm, we could see that the system performance improved, the system seismic resilience performance improved by 6%. On the right side, you can see the DTON water network and the epicenter for the worst case seismic scenario. And genetic algorithm shows after assigning only $10 million budget, the system improved 8%. Another question that might come up is why 15 million for one and 10 million for the other? And the answer is because of the different scale. So the XNet was almost as 5 times bigger as the DTON. So coming up with 15 million and 10 million would be basically relatively reasonable. Some discussion point for this study. Basically, our sensitivity results shows a spatial hazard uncertainty, like your epicenter location, the event magnitude, and the soil stiffness are the primarily drivers of your resilience variability. Basically, these parameters are the most important and most sensitive variables that you need to take care of. Also, the CIPP rehabilitation under a budget constraint plan contribute to improvement of seismic resilience by 8%. And another interesting observation was usually the reinforcement happens and would be concentrated around the epicentral location. So when on a very seismic area, you should prioritize your CIPP rehabilitation around your faults, around the areas that you expect the earthquake happens the most. The results of these studies for the first phase is under publication, is already accepted and under publication on Journal of Pipelines, Systems Engineering and Practice. And for the second phase, the results have been submitted to Tunneling and Underground Space Technology Journal, and you can see the remaining references that I used for this presentation. Thank you very much for your attention, and I'm here for any questions and any discussion.
Thank you, Mahmoud. It's an informative presentation. So for any of you attendees, if you have any question to Mahmoud about his presentation, you can type in your question and we'll take it up. We have one question here is asking, does bedding and cover have any impact on results?
I'm sorry, Justin, can you repeat the question? I have a hard time listening.
He's asking if the bedding or the cover of the pipe have any impact on your results for your analysis.
It definitely can have effect on the results. It wasn't like a parameter that we could use for the sake of our probabilistic assessment, but it is a very good. It can be a very influential parameter in case of you have a specific bedding or cover. But what we did was basically trying to have different soil classes to cover a different range of grounds and beddings for our assessment.
Thank you. The next question is, what is the probability of correctly predicting the epicenter of the seismic event?
So this is like very hard to predict like where would be the next location of your earthquake, and usually in those cases you have to come up with seismic random scenarios, and that's why we did 10,000 seismic random events. Basically, what we wanted to do is to cover a very wide range of different epicenters and different locations and see what would be the average damage or average seismic resilience that the system can have.
Thank you. The next one is there a similar study for other material pipe, such as clay, PVC, or concrete?
There are, for example, in case of network analysis, there are. However, what they use generic, like available literature available fragility models. So if you go and look for those models, you can see for example, for its different range of pipe sizes, they are using the same equation, which might affect your results to some extent. Or they do not consider different soil classes, which in our sensitivity results this is one of the most important variables here. So there are, however, in case of checking if CIPP how CIPP can affect those materials on a network level, to my understanding and to my research, there aren't that much research, and there's a huge gap for that.
Sounds like a good direction for future research too. Okay, the next question is, what fragility curves are generally used in network studies, and how do your curves compare?
So usually these fragilities there are a lot of fragility for 6-inch pipes, and a lot of studies are using these 6-inch pipes for different set of pipe sizes. And we also have a different fragility models for different pipe materials as well. But again, there's a huge gap to exploring pipe sizes and soil classes here. And next step can be different joint types as well. One of the important difference between my results and previous literature results, except from being more specific to sizes and also soils, is that my results showing the higher repair rates, higher failure rates in a same seismic magnitude, basically, if you compare my results to the previous results. And it couple reasons can be explained that. First of all, I used near field earthquakes, which is basically a little conservative. But if you want to come up with a 50-year management plan, you should be as conservative as you can be. So that's one thing. And also my FE model is my FE model was validated, and it compared our result. I compared the results with experimental and numerical, and we could confirm the reliability of these models. So the model is accurate by itself. On the other hand, we developed this fragility based on real seismic events. One thing that a lot of researchers have done was using some experimental and sinusoidal waves in order to develop the fragility relations rather than using a real life seismic events, which was something that this paper did, not by only one, but for 12 earthquakes for each soil classification.
Thank you. Maybe this one as last question, and we will move to Freddie's presentation. There's one more question we'll cover. When a cast iron pipe with CIPP already installed still does break, you can cut and install a replacement iron pipe segment. But what does happen with the then interrupted CIFF?
Justin, could you repeat the question? I'm also trying to find the question myself, but I'm having a hard time.
Okay, it's on the bottom of the screen. I'll read it for you again. When a cast iron pipe with CIPP already installed still does break, you can cut and install a replacement iron pipe segment. But what does happen with the then interrupted CIFF?
And by CIFF, you mean?
I am not sure about this question. Are you familiar with this?
I'm not familiar with CIFF. So,
if not, then let's have the person to ask you more in our question through email, and then we will take it up in that way.
Yeah, that would be great. That would be great, and I appreciate all the questions and all the time.
Okay, thank you, Mahmoud. It was a good session, and now we will move to Freddie's presentation, and I'll just change the slide. And Freddie, now the floor is all yours.
Justin, thank you very much, and thank you everyone for joining us today. My name is Freddie Diaz Duran. I'm a postdoctoral fellow working at the University of Alberta, and my role here is to lead all the research initiatives for the CUIIC, the Canadian Underground Infrastructure Innovation Center. So we're going to talk today about greenhouse gas emissions in Canadian underground infrastructure. Some concepts that we are going to consider, like modeling methods, standard decision frameworks, is what we are going to focus on today. So the presentation is going to have basically 7 parts. Some of these parts are kind of short, really short, but necessary to understand what we are talking about. But we're going to try to focus on parts 4 and 5, which are like LCA modeling, life cycle assessment modeling, and decision frameworks for life cycle assessment. So first, underground infrastructure is the core of our research at CUIIC. We are highly interested in this topic because it's let's say, underground infrastructure systems are not independent like individual assets. They are like systems composed of many components, and they are important because they enable essential services for the cities. They are responsible for energy, for water supply, for transportation. And so all the resilience components of the city services are relying on infrastructure that is underground. Second, they support like public health, mobility, energy reliability, and that's also very important for the city, for any city on Earth. And the importance is that because these systems are going to be underground, they are going to be buried there. Whatever is the decision that we make at the moment we are designing or building these systems is going to have consequences that last for decades. Well, so we are going to install a pipe for made of certain material. So that decision is like carrying a lot of emissions that are going to be there for decades. So we need to make wise decisions while designing, and that's why it's important to understand underground infrastructure as systems. Now, what is exactly what are GHG? GHG stands for greenhouse gas emissions. So when we say GHG, is basically that. GHG are multiple gases, and those gases are like CO2, CH4, N2O. Those gases, because they are like the units to measure those gases are so different, we try to convert them into an equivalent measure of carbon, and that is why we use the global warming potential, GWP. The global warming potential is nothing but converting every other gas into carbon. So that is why we talk about carbon equivalent when we talk about GHG emissions. So GHG is also, it's important to understand that can be separated between embodied carbon and operational carbon. So whatever is, let's think about any asset, whatever is related to the operation of the asset, that is operational carbon. We are not going to focus on that part of the carbon emissions at this point. We are mostly interested in embodied carbon. Embodied carbon are those emissions coming from material, transportation of the materials to the construction site, for example, the construction site, the construction activities itself, and any physical intervention that is required to sustain the asset once it's constructed. So basically, maintenance, rehabilitation is also there, but nothing related to operational, just what is necessary to create and sustain the asset. It's important to be clear about that separation. Then the third thing that is important to consider now is the life cycle assessment. A life cycle assessment is just a method, a structured method that we use to quantify environmental impacts across all the stages of any system. So, oh, please don't move my slides. Okay, so think about any system, then we can consider the life cycle of the system, of the assets, can be like separated in different stages. In the graph, in the image over there, you can see we have a product stage, for example, a construction stage, operational stage, end of life stage, and the beyond system boundary. Basically, this separation is according with some standard. We are going to discuss a little bit of standards in a few minutes, but it's important to understand what life cycle assessment is. It's just a method to quantify environmental impact. In this case, the impact is GHG emissions. So what we are interested is in quantifying GHG emissions along the life cycle of the assets. Now, when we are dealing with life cycle assessment, there are many ways to approach this problem. That is why we are going to focus a little bit on this part, modeling. How are we going to model the GHG emissions? How are we going to quantify those emissions? So the first thing we need to consider to understand this modeling of a life cycle assessment is what is the approach that we are going to take when dealing with life cycle assessment in underground infrastructure. Different assets, different systems can be approached in a different way. It's not the same if you try to approach the life cycle assessment of a building or something that is like built on the surface and something that is underground. Different approaches are necessary, and some adjustments are necessary, and that is kind of what we are facing right now at CUIIC, and that is why we are interested in this discussion. So approaches basically can be attributional or consequential. Are basically how are we going to consider that the asset is responsible for the GHG emissions? How are we going to do that is going to define what is the kind of approach, and we are going to discuss more of that. Then we can move to methods. Methods are basically the modeling frameworks in the sense, or the modeling considerations that allow us to get the numbers, and that's what's important for quantifying GHG emissions. And then we can move to techniques, and techniques are basically implementation tools, which are allowing us to approach the calculation of those emissions in different ways, like dynamic or probabilistic. So we need to consider also the techniques. For the approaches, let's say that there are two basic approaches, and for underground infrastructure, we are considering the attributional and the consequential. Attributional approach is basically when you have a system and you have a clear identification of the components of that system, what you do is you quantify environmental burdens of the system using what could be like the best available representation of the processes that were used to build or to create that asset. And based on that, you can quantify the emissions. So basically what you're going to do is you're going to quantify materials, you're going to quantify processes like excavation, for example, and then apply some factors, and based on that, you can get GHG emissions. So what you are doing is you are attributing emissions to specific components of the system. And you can do that for systems that are already built, but also for systems that are going to be built, but for projects, basically. When we talk about consequential is a little bit different, because what we want to see here is if what happened if we change something. So basically what a consequential approach allow us to do is to compare, to make analysis of different scenarios, to estimate how much is going to change in the emissions if we modify something. Like, for example, if we want to build or install a pipe, what is the consequence of changing from open cut to trenchless technologies? That is just a basic example, but is what is going to be considered. Now, when we go to the methods are a little bit like confused sometimes in the literature, and it's important to be clear on that. It's like one thing is the approach, the other thing is the method, and now we are going to talk about techniques, so that's another thing. So the methods are basically how are we going to consider the calculations. So for the methods, we are seeing here three different methods. The first one is the process-based method, which is basically also known as the bottom-up modeling. What we do there is we quantify all the materials or the quantities, all the unit processes and physical flows, and multiply those quantities for times emission factors, and we get the GHG emissions. Like the traditional way we do it for attributional, for example, is very highly is quite common to use this method for that application. But also there is another approach. What happens if you don't have quantities? What happens if you don't have everything that you need for that approach. Then we can use another approach, which is the input-output approach, or the input-output method. In the input-output method, we are now using what is known as top-down modeling. In top-down modeling, what we are doing is basically using economic input-output tables to quantify the emissions. So in that case, we don't have all the emission factors. What we have is emission intensities, and we're going to see an example. And so what we say is how much are we expending, how much money we spend in this asset, and how much in different activities while building the asset. And based on those numbers of money, we consider emission intensities and convert that into GHG emissions. So in the first approach, process-based, we consider mostly materials and processes. In the second approach, we are considering mostly money. How much does it cost? And based on that, we are calculating emissions. The hybrid approach, the hybrid method, is a different one, which is a combination of the process-based and the input-output based. And the best way to explain that is perhaps with an example. So let me just try to, or before we move to the example, let's first explain the techniques, because we are going to need those techniques at some point. So we're going to consider this in an example, but let's move to the techniques. So we have talked about the approaches, we have talked about the modeling methods, and now the modeling techniques. For the modeling techniques, we are basically considering dynamic, probabilistic, spatial explicit, and parametric LCA. So basically, in this case, what we are saying is, are we going to consider the time in the process, how like variables change with time? If we are going to do that, we are like including models that are dynamic. And that is a different approach. If we consider just a static approach, it's like nothing is changing, just one specific value. So dynamic is considering the variation in time. But also we can consider the probabilistic approach, in which we are considering uncertainty and variability in the parameters. And then we can use calculation techniques like Monte Carlo simulation, for example, just to consider how the uncertainty affects the results. So different techniques are these. But also we can consider the spatial explicit technique, which is basically differentiating between different geographic contexts. So location can impose some specific conditions for the calculations. The factors, for example, is not the same the energy that is generated in Ontario, for example, and the energy that is generated in Alberta. So one of them is based on hydropower and the other one is mostly in oil. So though that is going to create a difference in the calculations. And the parametric LCA is allowing us to basically consider or formulate the life cycle as an explicit function and then analyze all the parameters in that function and see how those parameters affect or are impacting the result. So different techniques. We have approaches, we have methods, we have techniques. This slide is just summarizing that: approaches, modeling methods, modeling techniques. If we see one example, a short example, what we are seeing here is a tunnel. We are going to use the attributional approach, and the system boundary in this case is cradle to side. We are just considering stages A1 to A5. And for the functional unit, we are considering 1 kilometer of the tunnel as a single bore, large diameter transit tunnel. We include excavation, segmental lining, track slabs, installation. Some dimensions are here. Basic example just to show you how to apply, for example, the process-based method. In the process-based method, we take each activity like excavation, segmental lining, track slabs, and we quantify those activities, for example, in meters cubed, And then we apply an emission factor, and by multiplying those two, we are getting emissions, which are kilograms of CO2 equivalent. If we add them up, we are getting the total emissions for that functional unit, which was 1 kilometer of tunnel. It's a basic operation, just quantities times emission factors. Then if we move to the input-output approach or method, what is happening is that we are no longer interested in the emission factor itself. We are mostly interested now in how much was spent in excavation, how much was spent in lining. And then we use emission intensity factors, and those emission intensities are going to give me the possibility to calculate the GHG emissions. So in this case, because of the emission intensities, I'm getting a lower value, in this case 3.6 million or 3.6 tons of CO2 equivalent. The hybrid approach is kind of a combination of the previous two. And that approach is allowing me to consider, for example, an overhead of indirect cost, things that were not considered in the process-based approach. And by considering a percentage of that indirect cost, what I'm doing is getting an extra value to add to the process-based result, and we are getting a little bit more of GHG emissions when we compare the results. So basically, if in this slide you are comparing the three methods, you are seeing that the process base is giving you something like 5.5 tons of CO2, while the input-output method is about 3.6 tons, and the hybrid is a little bit higher, like 5.5% higher than the process-based method. Those are methods. But now, when we are dealing with this life cycle assessment in underground infrastructure, we need to decide, or we need to discuss decision frameworks. And the best way to define a framework, a decision framework, is how are we going to calculate those life cycle, those GHG emissions along the life cycle of the system. In order to do that, we need a framework, to define a framework that is allowing us to, or let's say, to be procedural, to be integrative, to be standard line, and to be decision-oriented. Basically, what we want is that the framework we are defining organizes the sequences of activities or the flow work that allow us to consider all the things that we need to account for the GHG emissions. We are going to do that in an integrative way, which means that we are going to consider every single activity in the design, and we are going to convert that into an impact, which means into a GHG emission. By doing that, we are for sure, we need to be standard aligned, and all these three things are going to make me, or to allowing me to make decisions. If the GHG emissions are too high, then I can change something in the design. And by this approach, with being integrative, is allowing me to change things that are actually reflecting into lower GHG emissions. So these are examples of frameworks for you to know. The RIGS, for example, and the PAS 2080 are examples of frameworks. We also have standards. We all know many standards like ISO, for example, EN, or the Canadian standards, ASTM, even American Society of Civil Engineers have some pre-standards. Those are standards. The standards are basically a consensus-based normative document which basically establishes requirements, rules, or guidelines to ensure consistency, comparability, and quality in the process, methods, or results. So these are examples of standards, just for you to know. There's also guidelines, and guidelines are allowing us to understand how to use the standards for some specific application. So these are examples of guidelines. Two Canadians, one is the last one is the GHG protocol, which is from Europe. Basically, what we see here is that we have, in order to define a framework, we need to consider the standards and the guidelines. But the framework is like the first level of analysis, which is allowing me to consider all these things. I think I will stop there, and I will let the time for questions. Justin, please.
Thank you, Freddie. It's informative, and I can see there's lots going on. So we have one question in here. Does your LCA modeling consider the money saved with a lower cost installation method could be directed to other GHG reduction approaches with a higher return?
Okay, let me understand the question. Does the LCA modeling consider that the money saved with a lower cost installation method could be directed to other GHG reduction? I'm not sure what the question is asking, but let's say when we have these methods, let's say the approaches are attributional and consequential. When we consider the consequential approach, what is happening is we are considering different scenarios. And by different scenarios, we are, of course, considering different activities. And different activities could mean, for example, different costs. Like you are saving money in one of those installation methods, for example. Okay? But more than money, what we are, of course, money is usually what is more like driving the decisions in engineering a lot of times is money. But if we are thinking about how to reduce GHG emissions, what we are thinking is what are the materials or the processes or the techniques, technologies, whatever it is that we can apply that is allowing me to reduce the number of emissions. When we use that consequential approach is that when we can consider that. But now that we have this consequential approach, we need to move to the methods. How are we going to approach, or how are we going to calculate the GHG emissions? So for the methods, we had this process-based, input-output, and hybrid. For the process-based, we are not thinking about money, and that's important to be clear. It's like in the process-based, we don't talk about money. So if you have a consequential approach and you have all the data to actually get amounts of material, quantities like excavation, or the fuel being used, or I don't know, the machinery times, or you have all the parameters, you can use this process-based approach or this process-based method without considering any that is related to money. So decisions are not made based on money, but based on GHG reduction. But of course, that is what I was saying. GHG is not the only driving in the decision of an engineering project. So you have to consider also money as well at some point. But on the other side, when you have the input-output method, what you are considering is money. In this case, you are not interested in emission factors, or maybe you are not that interested in small details or processes, but you are interested in how much did I spend in this excavation or in this tunnel lining. And that is what is allowing me to consider money. In that case, money is important because is a fundamental input for the calculation of GHG emissions. I don't know if that was a good response for the question, because I don't really understand the last part of the question.
Thank you, Freddie. For the time being, maybe one more question will take it up. Another question is, do your models consider parameters such as high friction losses with some material equaling higher pumping cost, expected life with different materials, repair frequencies, costs with different materials, for example?
Yeah, that's a great question. That's a very nice question. And by showing you this slide, one of the projects we are working at is tunnels, for example. And every time when we are going to like face one of these projects, what happens is that we need to consider what is the role of the infrastructure. What are the components of the infrastructure system, and what is how much are the emissions associated to each component? So that's kind of the percentages that we can find, we can allocate when we do the analysis. But this is not exactly for water mains, for example, because I see the question is more related to water mains. I don't have a slide for water mains, but let's think about the same thing. We consider then what is the most important thing or the main driver for GHG emission when we are dealing with water mains or water supply systems. So once we have the main component, the main driver, let's say the pipes, in that case, then we start doing the analysis, a very high detail analysis, like considering things like that, like what happened with the friction losses inside the pipe, or what happened with the pumping cost. That is also analysis. In order to consider those aspects in the calculations, we need to consider basically this process-based approach, process-based method. If we use the process-based method, we are going to consider friction losses, we are going to consider pumping cost, everything is going to be considered here. But if you are using the second method, the input-output method, that is going to be more general. We are not that interested in pumping, in pumping specific costs. We are mostly like or how much is the pumping associated to the friction losses in the pipe. We are not in that analysis. We are just in general how much we spend in pumping, and that pumping is going to be part of the calculations. But remember, we said at the beginning that when we talk about pumping, is most about operational carbon. And we are not in this presentation focused on operational. The analysis could be similar, is what I'm trying to say. You can use the same methods, you can use the same techniques to do the calculations, you can try to follow the same things, but pumping costs are mostly operational, and we are mostly focused on embodied carbon.
Thank you very much, Freddie. And for this moment, I would like to acknowledge CUIIC members listed in here in this screen. And I also appreciate everybody for being here for our webinar, and hope you have a good rest of the day. Thank you.